In this short video we're going to be looking at the effective capacitance when we have two or more capacitors in either series or parallel. You see something very similar to this with resistors. If you remember in year 12, if you have resistors in series or resistors in parallel, there's two equations for calculating the total effective resistance. We're going to do exactly the same today, except we're going to be using capacitors. Right, we're going to measure the capacitance of the network with a multimeter. Now, not all multimeters can do this, but this one can. It can measure capacitance as well, connected to these two terminals here. Right, we have to be mindful, because we're using electrolytics, we have to be mindful that the negative terminal is connected to here. Okay, well, I've got three different sizes of capacitance. I've got 100 microfarads, 4.7, 2.2 and 1.0 microfarads. The only drawback with using the multimeter is multimeters can only measure very small values of capacitance. So that's why I've only gone up to 100 microfarads here. Okay, but if we take the 100 microfarad first, let's just have a look at this on its own. Okay, you should be able to see there 100 microfarads. Now, which terminal is the negative? You'll notice on electrolytics there's a negative symbol on a grey bar, so that this terminal here is the negative terminal. Okay, right, if we get that connected in and connected to the crocodile clips, we should see that looking at about 95 microfarads. Okay, so that's quoted as being 100, but in reality we've got 94.8 microfarads. Okay, so assuming that this is fairly accurate, it just shows you that there is definitely a plus or minus. There's definitely a tolerance in values of quoted capacitance on capacitors. Right, now let's start with networks. Let's start with measuring pairs of capacitors. Now I've got a couple of 2.2s here, so I'll start with these. Okay, let's start with these. Now, let's go for parallel series first. Okay, so we want the negative there. We want the positive there. And we want to connect those in series. So already we can see that the two in series, these are the two 2.2s in series, the effective capacitance is 1.110 microfarads. Which is interesting, because I'm sure a few of you were expecting the effective capacitance to be 4.4 there, but it's actually 1.1, it's half, isn't it? Now, let us now, okay, there's the two 2.2s, let's have them in parallel. Now to do that, we need to connect them like this. So now we've got, hopefully you can see that, we've now got the two capacitors in parallel. Okay, now the effective capacitance is 4.42. Okay, so already we can see that it's now doubled. Having the two 2.2s in parallel has doubled the effective capacitance. Okay, so they were two 2.2s. Let me show you that. you go, 2.2 microfarads. And the other one, 2.2 microfarads. Okay, right, so that is your first couple of results for your table. Right, now let's mix it up now. Okay, let's go with a 1. Let's go with a 1 and a 2.2. Right, so there is a 1 microfarad capacitor. Good. Right, let's go. Doesn't matter which order here. So that's the 1 there. Let's go with a 2.2 there. Right, so let's put them in series first. So putting those in series is just a case of connecting like that. Right, there you go. So we've got a 1 microfarad and a 2.2. The effective capacitance is 0.711 farads. Okay. Now let's put these two in parallel. Okay. So again, doesn't matter which order or which one is on the left and which is on the right. There you have it. So there's your effective capacitance of the two in parallel. So we've got a 2.2 and the 1, and the effective is 3.26 microfarads. I think you can start to see the pattern already, hopefully. Well, which was which? So that was the 1, and that was the 2.2. Okay, let's go with the 4.7 and the 1. So now we have a 4.7 microfarad capacitor. Just about to see it there. Okay, so there's a 4.7. Right, again, we'll have the 4.7 at the top. We'll have the 1.0 at the bottom. And then we need to connect them. Right, two in parallel, in series, rather. In series, we've got an effective capacitance of 0.850 microfarads. Now, let's put these two now in parallel. It's a little bit fiddly, but if we just give them a twist, that helps. Okay, so now the two capacitors are in parallel. And there we have it. So we've now got a 4.7 and a 1.0 in parallel, and the effective capacitance is 5.53 microfarads. Okay, last but not least, let's see what the 100 does. So that was there and that was there. So let's have a look at the 100. Let's try 100 and a 2.2. So there we have 100 microfarads and 2.2. Right, let's do it in series first. So the 2.2 can go at the bottom, the 100 can go at the top. And we want to connect. This third crocodile clip, I think you probably figured that out, that's just to connect those together. Right, so there you have it, 100 microfarads and a 2.2 in series, 2.16 microfarads. Okay, so get that into your table, and finally, let's see what happens when these two fellas are in parallel. There we have it. Okay, so in parallel we've got a 97.3 and so 97.3, that's the total effective. Right, now that looks like to me that 100 is not right, is it? So let's check that. Okay, one last thing that would be worth doing, I think, is to go through and check these individually. So the 100, the effective capacitance of the 100, sorry, the actual capacitance of the 100. Yeah, there you go. So that's quite a bit off, isn't it? So that's the value that needs to go into your table. So 95.2 is the actual capacitance of that fella. Now the 4.7, let's see how close this was. The 4.7, again, 4.49. It's a little bit off, isn't it? Now the 2.2s, let's see how close they were. Okay, that's closer, isn't it? So one of the 2.2s was 2.21. And that's 2.22, so yeah, thankfully they're fairly close. And then finally the 1.0, let's see how close that was. .045. Yep, so they're not bad, but quite a significant difference with that one. Right, there you have it. What's the pattern? What are the two equations? Thank you.